Good morning. Today we're going to start talking about Chapter 9 in our text, which is entitled Inferences from Two Samples. What we're going to be doing in this chapter is drawing two different samples from two different populations, and thus we can use statistics principles to test the claim that certain characteristics of between these two populations are the same or perhaps different. In other words, we can test a treatment group versus a control group. Section 9.2 is entitled Two Proportions. And in this way we can take two populations instead of one. I'll call this population 1 and I'll call this population 2. And let's say we're investigating some characteristic in both of these populations. You pick one out of a hat. You could say left-handedness, or you could say we're checking the cancer rate from these two different populations based on where people live, perhaps near power lines or something like that. Alright. Population 1 has a population proportion with some characteristic of interest, and I'll call that P sub 1. Population 2 also has a population proportion with the same desired characteristic of interest, and we're going to call that P sub 2. And in wide strokes, the idea here is we're going to be testing the claim that P1 equals P2. Do these two population proportions, are they the same? Are they different? Is one less? Is the population proportion from the treatment segment of the experiment greater or less than the control population proportion, etc. So a bit more formally, we will test claims of the form and the null hypothesis will always be of this form: H sub 0, does P1 equal P2? In other words, this is the claim that the two different population proportions are the same, are indeed the same. Okay, that's an E there. Alright, well, that means the alternative hypotheses will be one of three types. Well, either P1 is less than P2, the population proportion of population 1 is less than the population proportion of population 2. Either P1 is greater than P2, or of course P1 is not equal to P2. Alright, so we'll be testing H0 claims versus H1 claims, somewhat similar to our hypothesis test framework that we've seen in the past. Okay? Alright, we're going to use our TI-8384 calculator. And again, similar to operators we've used in previous sections, the TI-8384 calculator will compute p-values in this context, but using a different operator. It's going to be called the Prop ZTest command. Prop because we're dealing with two proportions from two different populations, and you find this under the stat menu. You hit your stat button, and then the test options, highlight and select from the test sub menu, and then you'll scroll down in that sub menu and you'll find the Prop ZTest command. Alright, well, before we punch out some examples in this regard, let's get some notation down. Alright, let's say we've got population 1. As we've said before, the population proportion with some desired characteristic of interest we want to put under test, like cancer rate, like left-handedness, like having blue eyes, whatever, we'll call it P sub 1. Now we're going to be drawing a sample from this population 1, and N sub 1 is going to be the sample size, the number of elements in your sample. X sub 1 is going to be the number of successes, or the raw count of successes in your particular sample. Now P1 hat, not P1, but P1 hat is going to be the sample proportion with that desired characteristic. Sample proportion with desired characteristic of interest as drawn from sample in population 1. And Q1 hat, I'm going to be writing this down to establish some formulas. It's just the probability complement of P1 hat, much like we saw in the binomial distribution. Alright. Population 2, again, we're going to be drawing another similar sample from population 2 and comparing. And of course, as you might expect, I won't label all these. There's similar notation. Hang on. Similar notation for all these parameters in population 2. X2, P hat 2, and Q2. Oh, I ran out of room at the end. Q2, I want to squeeze in there. And they're similarly defined as in the first population, so I won't bother writing down the definitions. Okay? Well, let me do write something here. The sample proportion is always your raw count of number of successes divided by the sample size, but I'm betting we already knew that. Okay? Alright. I want to talk about some formulas here. Now, they're somewhat complicated, but don't panic. We're not going to use these formulas in a pen and pencil kind of way. I just want us to be aware that the calculator will compute these values upstream. So let me get a fresh screen. Alright. There's such a thing as a pooled sample proportion. That's P bar. That's really the sum of raw counts of successes from both populations divided by the sum of the two sample sizes. Q bar, not hat, Q bar is 1 minus P bar. And our Z statistic, our Z value in this sense, is going to be really the difference in the sample proportions minus the difference in the assumed population proportions divided by this nasty looking thing, P bar Q bar over N1 plus P bar Q bar over N sub 2. Alright, now don't panic. I just want you to know that this p-value that we're going to compute with our hypothesis test operator to Prop ZTest is based on a z-score. So the calculator computes this. You don't have to do it from first principles. And we'll run through some examples before we're done today. calculator does this via the 2 Prop ZTest. Alright, remember it's the 2 prop because we're dealing with 2 proportions from 2 different populations, and Z-test because this operator bases its values on a z-score or z-value. Okay? Alright. I want to look at example 1 on page 444. Let me turn there myself, and you might want to turn there also. And basically, we're investigating the idea that large denominations of money gets spent less than smaller denominations. In other words, people tend to be more likely spending the same money in smaller denominations. Well, we'll see. I'm reading from page 444, example 1. In the article, The Denomination Effect, researchers reported results from studies conducted to determine whether people have different spending characteristics when they have larger bills, such as a $20 bill, instead of smaller bills, such as $21 bills. In one of the trials they conducted, 89 undergraduate business students from 2 different colleges were randomly assigned to 2 different groups. In the dollar bill group, 46 subjects were given dollar bills. The quarter group consisted of 43 subjects given quarters. All subjects from both groups were given a choice of keeping the money or buying gum or mints. The article includes the claim that money in a large denomination is less likely to be spent relative to an equivalent amount in many smaller denominations. Let's test that claim using a 0.05 significance level with the following sample from the study. Alright, so let me copy down the table that's in our book on page 444. It'll only take a minute. I'll abbreviate things a little bit. You might want to look at the table yourself in the book for a little more detail. Alright, so all the subjects were given either a dollar bill or 4 quarters. The group that got the $1 bill we call group 1, and the group that got 4 quarters we call group 2. Alright, we've got the count, the raw count of people in each group that spent the money. In group 1 there was 12 that spent the money, and the size of group 1 was 46. So 46 people were given $1 bills, and 12 of those spent the money. In group 2, well, the raw count of people that spent the 4 quarters is 27. And the sample size, the number of people receiving the 4 quarters, was 43. Alright, so we're going to, again, test the claim. That the same amount of money, I'll abbreviate that with same money, in a larger denomination, namely the $1 bill, is less likely to be spent. Alright, we can do that with the 2 Prop ZTest command. Alright, I'm going to have to scroll down. You might want to keep that table in your eye and on the side here. Step 1. We're going to have our familiar 3-step process or 4-step process, depending on your point of view. Step 1. I'm having trouble here. Need a bigger eraser. Alright, step 1. State the hypotheses. And remember, we've got two groups, two populations here, really. Those who receive the larger denomination and those that receive the smaller denomination. All right, we're going to conjecture that the proportion of people that spend money is the same for both populations. Now, we want to test the claim that the same money in larger denominations is less likely to be spent. Well, remember, Group 1 was the larger denomination group, so we want to test that against the alternate claim that the proportion of people who spent the larger bill is less. And so that would be the alternative claim. Alright, so this is going to be a left-tailed test. Left-tailed hypothesis test, and we're going to do it using a z-score, and we're going to do it using our 2-prop ZTest command. Alright, step 2. Compute the p-value. Again, we're going to use the 2-prop ZTest operator on our calculator. Alright. To get there, we press our Stat button, highlight and select the Tests sub-option, scroll to select this 2-prop ZTest command, and hit Enter, and you'll get a screen prompting you for the following information. It should say 2-prop ZTest on the top of the input screen. It prompts you for some familiar looking things. And the framework looks somewhat familiar to what we've seen before in Chapter 8. Well, X1 is going to be the raw count from Group 1 with our desired number of successes, and you may recall from the table, 12 people spent the entire $1 bill in Group 1. And N1 is the sample size of Group 1 with that treatment, and 46 was the sample size. In Group 2, again from the table, you recall there were 27 people that spent the 4 quarters totally, and there were 43 people that received the 4 quarters in Group 2. Alright, then we've got to pick the type of test, and this is the TI shorthand. Alright, we're going to be doing a left-tailed test, so we want to test the claim that P1 is less than P2, because that's the way the problem was worded. So highlight and select less than P2 on your input screen, and then calculate. And you should receive the following output screen. Well, again, it'll say 2-prop ZTest on the top, reminding us of what command we're using. It does give us the alternative hypothesis then. And the p-value, again, I wish this was a little more obnoxiously noted in the output screen. It's just a little p. It really should be a higher case p. It's 2.439 and change. E minus 4. Now, don't panic. That's just scientific notation. So I'll move this decimal place 4 places to the left, as indicated by this scientific notation. So converting to regular decimal notation, I get 0.0002439. That's my p-value for this experiment, for this hypothesis test. Alright, so step 2 is done. We've computed the p-value. Of course, now step 3, as in Chapter 8, we compare and make a conclusion regarding H0, right? Always, our conclusion is always in terms of H0. So I'll make this little mini table again, compare my p-value to the alpha level. The alpha level is given to us as 0.05 in the problem context, and our p-value I'll round off to 0.0002, because you can see quite clearly this is a very small p-value, and your p-value is less than alpha. And recall from chapter 8 that small p-values suggest H0 is false. Doesn't prove it, but suggests it. All right? So our goal here, or our conclusion here, I should say, would be to reject H0, the claim that population proportions are the same. All right, so if we're rejecting this claim, well, we're really saying that the people with larger denominations spend their money at less of a proportion or less of a rate than those with smaller denominations. All right, let me write this down, and it's an interpretive statement. Interpret. There is sufficient evidence to support the claim that the population proportion of people that spend the same money with larger denominations is less than the population proportion of people that spend the same money with smaller denominations. I.e., in other words, there is sufficient evidence to support the claim that people with larger denominations, I'll abbreviate that as denoms, of money, of same or equivalent monies, are less likely to spend. Okay? Alright, so that's how our Prop ZTest command works. And I want to punch through a couple more examples, do a right tail test and a two tail test. Next one I want to look at is exercise 7 on page 450 in our homework list. Turn there myself. Alright, here it is. Dreaming in black and white. Well, some people dream in black and white, some people dream in color, some people do both. I'm reading from the book, number 7. A study was conducted to determine the proportion of people who dream in black and white instead of color. Among 306 people over the age of 55, 68 dream in black and white, and among 298 people under the age of 25, 13 dream in black and white. We want to use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. Now, let me summarize some of those numbers we were given here in this problem. We have 306 people in our over 55 group, and from that group 68 dream in black and white. We've got 298 people in our under 25 group, and from that group 13 dream in black and white. Alright, so we want to use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. Let me write that down. Use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than, so that tells us what kind of test it is greater than the proportion for those under 25. Alright, I'm going to have to go to a fresh screen here, so keep all those data right next to you in your book on page 450, and I'll go to another screen. Alright. Step 1. We're going to state the hypotheses. Alright, I'm going to let the over 55 population be population 1. And I'm going to let population 2 then be the under 25 group. Alright, we're taking our sample, and in our sample we've got 306 people chosen, and from this 306 we've got a raw count of 68 over 55 people that dream in black and white. Similarly, in the under 25 group, we've got 298, and the raw count, I'll call it X sub 2, of people that dream in black and white from this group is 13. Alright, I'm going to state the hypotheses now. The hypothesis is, the null claim is that the proportion of black and white dreamers are the same in both populations. Now we want to test the claim that the proportion of people in the over 55 group is greater than, right? P1 greater than P2. Yeah? So there is our hypotheses stated. Step 2, compute the p-value. And for that we will use the 2-prop ZTest command. Alright, so we'll go a little quicker this time. You click Stat and Tests and scroll down to find this command. We are then prompted for X1, N1, X2, N2, and the type of test. Right. X1 is 68. Remember, group 1 is the over 55 group. The sample size for the over 55 group is 306. The under 25, the raw count of black and white dreamers is 13. And the sample size for the under 25 group is 298. And again, we're testing that P1 is greater than P2, so you want to highlight and select greater than P2, and then highlight and select your calculate command to get the following p-value in the output screen. P-value, again, that's a lowercase p indicated on the screen, and that's 6.01 times 10 to the minus 11th power. And now don't panic, that's scientific notation for a very, very small number. It's a 601 and a decimal point with 10 zeros in between them. If I move the decimal place over 11 places, very small. I would call this just 0 plus for all practical purposes as a p-value. Alright, so our p-value is computed. There it is. Step 3 would then be to compare and conclude. Make your conclusion about age 0. And to do that, you compare your p-value to your alpha level. Our alpha level was 0.01, but with this such a small p-value, I don't suppose the alpha level matters much. Certainly your p-value is going to be smaller than any reasonably chosen significance level. So we reject H0, the claim that the proportion of black and white dreamers is the same for under 25s and over 25s. All right, let me write that, summarize that in a brief interpretive statement. I'll claim there is sufficient evidence to support the claim that the proportion of people over 55 is greater than the proportion of black and white dreamers for those under 25. In other words, older people seem to dream in black and white at a greater rate. At least that's what the sample has suggested. Alright, I want to do another, I think 2 more exercises from our homework list. This one is exercise 8 on page 450. Alright, and this is a classic treatment and control group type problem. I'm reading for number 8 on page 450, ginkgo for dementia. The herb ginkgo biloba is commonly used as a treatment to prevent dementia. In a study of effectiveness of this treatment, 1,545 elderly subjects were given ginkgo and 1,524 elderly subjects were given a placebo. Let me write that down. 1,545 patients were given ginkgo, the treatment, and 1,524 elderly subjects were given a placebo, a control group, right? Among those in the ginkgo treatment group, 246 later developed dementia. Okay. And among those in the placebo group, 277 later developed dementia. Okay. We want to use a 0.01 significance level to test the claim that ginkgo is effective in preventing dementia. All right, we're going to do part A. In all these homework problems, we're only going to do part A. In other words, test the above claims using an hypothesis test. All right. Let me write that down, that very last part of the problem. So we'll use an alpha equals 0.01 significance level to test the claim that ginkgo is effective. Okay? Well, if ginkgo is effective, then the dementia rate for population 1 would be less than the dementia rate for population 2, right? Alright, so let me write that down. If I let the treatment group be population 1, I'm going to say the null hypothesis is then that P1 equals P2, and the competing alternative claim, well, if ginkgo is successful, then the dementia rate would be less for the treatment group. In other words, P1 is less than P2. So I state the hypothesis. Right? Now we want to compute the p-value. Again, we use our Prop ZTest command. I want to plug in x1. Well, that was from the treatment group. We had 246 dementia victims among 1545 subjects given the ginkgo. Our control group x2, we had 277 dementia victims among 1524 subjects. The type of test, well, we want to test the claim that P1 is less than P2, so it's going to be a left-tailed test. So highlight and select, and our output p-value from our output screen is 0.048. I'll just call it 0.048. Okay? Alright, so there's our p-value indicated by the above data. So now we want to compare and conclude. Our p-value is 0.048. Our alpha level, the book tells us to use 0.01, and certainly our p-value here is greater than our significance level. And we recall from Chapter 8 that large p-values suggest H0 is true. There's nothing wrong with H0. Alright, so our conclusion here is to fail to reject H0. Alright? In other words, there is not sufficient evidence to support the claim that dementia rate is less in ginkgo users. Let me write that down in a brief interpretive statement. There is not sufficient evidence to support the claim that our dementia rate or proportion is less for people treated with ginkgo. Okay? Alright, let's do let's see, I've got two more here. Number 9 and number 18. Number 9 is another right-tailed test, so I'm not going to do that. I'm going to look at 18. That's a two-tailed test. And that'll be enough for the day. So exercise 18 in our homework list on page 452. Let me read that. Excuse me. Talks about marathon and finishing marathons, in particular New York City Marathon. In a recent New York City Marathon, 25,221 men finished, and 253 dropped out. So let me write that down. 25,221 men finished, and 253 dropped out. Amongst women, 12,883 finished, and 163 dropped out. Alright, based on data. Use a 0.01 significance level to test the claim that the rate of those who finish is the same for men and women. Write that down. Use 0.01 significance level to test the claim that the rate of those who finish, write that down, that the finish rate or finish proportion, I'll call it, is the same for men or women. Okay. Alright, well, step 1, state the hypotheses. H0. Well, if I'm going to let P sub 1 be the finish rate for the men and P sub 2 be the finish rate for the women, I'm testing the claim that P1 equals P2. And the alternative then is that they are not equal to each other. It doesn't say which is more. We weren't asked to test the claim which is more. We are asked to test if they are the same. So this is going to be a two-tailed hypothesis test as implied in this hypothesis statement. Alright, we'll compute the p-value using our 2-prop ZTest command. And we are prompted for some things, but we've got to be a little bit careful here. X1. Well, if men is group 1, well, we want the total number in this group. We have to actually add these two values, 2521 and 253, right? This many finished, this many dropped out, which means we had a total of 25221 plus 253. So let me add that up quickly. 25221 plus 253 equals 25474. Oops, that's n, sorry. Forgive me, that's the n sub 1. The sample size, right? 25474, yes. Alright, now the number of finishers in the men's group, that is 25221 right here, right? So you're checking the finish rate or the finish proportion, 25221. Amongst the women, similarly, the sample size is the sum of these two values. So I add 12883 plus 163, and I get 13046. Be sure to enter it in the right row. And out of that 13,046, we had 12,883 women finishers. Alright, we now want to select the not equal to P sub 2 option here for our type of hypothesis test. And if we then hit calculate, we get a p-value in this hypothesis test of 0.0213. Let me get a fresh screen. I'll now compare the p-value to my alpha level. The p-value, you recall, is 0.0213. Our alpha level is 0.01. Certainly the p-value is greater than. So our conclusion, large p-values suggest H0 is true. So I will fail to reject H0. Remember, your conclusion is always in terms of H0. Alright, so if we fail to reject the claim that the men finish rate is the same as the women finish rate, we can write a brief interpretive statement that says there's not sufficient evidence to warrant rejection of the claim that the finish rate is the same for men and women. We cannot reject that claim. Alright? In other words, the difference between the finish rate for men and women is not statistically significant. Alright, it's been about 46 minutes. We'll call it a day. This concludes section 9.2, two proportions.